Multiverses today on Physics X. So if you're just joining in, this is Extraordinary Concepts in Physics. So if I can get to the next page here, where I review, possibly you do too, very interesting concepts in physics, trying to focus on the concepts themselves as opposed to the math behind the concepts, although sometimes can't get away from a little bit of the math. So these are online, several places, iTunes, on the web, and well, if you're in the class, you can see it through the class webpage. So multiverses are a word, multiverse, a phrase that I really hadn't heard when I was an undergraduate many years ago before fire was invented. So it was invented soon thereafter, and now is a relatively common phrase. I understand it's used a fair amount in science fiction. It is somewhat controversial, but it's really interesting. So far as I can understand, the initial idea came from Everett in his many worlds interpretation of quantum mechanics, but more recently it's been expanded by Max Tegmark, currently at MIT, into different levels. So it's a lot of fun to think about, but we'll get to the criticisms right at the end. So this is really mind-expanding stuff. So let's look at a level 1 multiverse. Well, a level 1 multiverse is really sort of just our own universe. It's just that it's our own universe supposing it is effectively infinite, or much larger. As you know, I consider infinite to be much larger than anything else that can be other scales in the problem. So it's possible that our universe is open, as we discussed in previous lectures, and the universe might have started even with an infinite volume or be picked up at some time with an infinite volume. Then its volume could have increased even greater with inflation. It could be that this universe we live in is extremely vast. However, we can only see a certain amount of it. We can only see the amount of it where light can come to us since the universe started. And it could be tremendously more vast than that. So we can only see a little bit. So currently you can only see around the room that you're in. But many of you believe there's actually things beyond this room and other rooms and a vast place some people call Earth. Well, in analogy, there's the visible part of the universe is only a small part of the universe. There's much more out there than can meet our eye. And all of these can be part of the level 1 multiverse. So in this universe, the physical constants would be the same, because we're going to change that later. And they're always the same. So the physical constants could be G, so we'll talk about that. However, as we'll see, there's an identical volume, or a nearly identical volume to ours, 10 to the 10 to the 115 meters away. So the general idea of this kind of multiverse is that the universe is so vast that everywhere in the universe you have atoms forming as the universe gets old enough and they form into people. So if you look at the universe just outside our observable universe, you'll see one that has very similar aspects to it. It has galaxies, it has planets and stars, but does it have people? Well, no, maybe not that one, because just the Earth, the solar system that would have formed the Earth, the star system would be a little bit different there. But okay, let's consider the one next over, and then the one next over to that, and the one next over to that. If you go far enough, you should be able to find a place where something like Earth formed. In a galaxy, something like the Milky Way. And if you go even further, you can find a nearly exact copy of the Milky Way with a nearly exact copy of the Sun, orbited by a nearly exact copy of the Earth. So your twin may exist far, far away. And not only that, if there's no boundary to the universe, you may have many, many twins out there doing very similar things to you. Okay, so I gave away the next slide. There are possibly, given that we don't know how big infinity is in this case, assuming it's truly infinite, there are infinitely many nearly exact replicas of you doing something slightly different, progressing toward a slightly different future than you are right now. So for instance, you might be planning on having something for lunch, whereas your twin, 10 to the 10 to the 115 meters away or further, might decide at the last minute to have something slightly different for lunch. And then you would be living a different life from your twin. But up until now, it's been exactly the same. This is different aspects of a level 1 multiverse. Strange, huh? All right, but you can make things more general. You can say, okay, well, in our universe, we know that the gravitational constant g is, what, 6.72 maybe times something, 10 to the minus, there's some units, 10 to the minus 11 or something. Didn't think I'd need to recall that just now. You can look it up. Maybe g in a level 2 multiverse is slightly different. So maybe there are other parts of our infinite universe. We're just in a bubble of this kind of g and this kind of Planck's constant h, and the speed of light is a certain amount c, and the fine structure constant lambda alpha is a certain value. Maybe all of those just happen to be the same, but maybe they're a little bit different. In a level 2 multiverse, there could be something a little different. So if h was a little different in one of these multiverses, you wouldn't expect to have the exact same replica of you. Exact replicas of you can only occur when all of the constants are the same in a level 1 multiverse. In level 2, things are different. But who's to say how many versions of h and g and c and alpha and possibly other constants that are currently unnamed and maybe even currently unknown, how many of them are known and how many possible values of them there could be? In an infinite universe, there could be realizations of all of these. So people have tried to think of some of these types of universes, and one is a chaotic inflationary epoch. May create universes of different bubbles where different rules hold different gravitational constants. Possibly, our own universe would be closed, which means that there's a finite volume in our universe, and it will collapse. But it may, due to physics that's not completely best understood right now, it may rebounce. And then we get another Big Bang. And then that comes to a close, and then there's another one, and another one, and another one, and there can be an infinite number. So maybe in different bounces, maybe you get to spin the random wheel on what h, g, and c are each time. And then you get a slightly different universe. And that would be another type of level 2 multiverse. Another one, called a fecund universe, if I'm pronouncing that right, is more internal to our universe. This one I haven't studied much. Black holes collapse, causing a universe to form inside. So universes that produce black holes proliferate, and you get a different way of coming up with level 2 multiverse. There could be other ones. Since this is so strange, it pushes the human imagination, and human imagination could possibly come up with other ways things are different. But this is only level 2. Let's get back on our elevator. And first I need to back up a little bit and say something that I was going to have a separate lecture on, and I should have given in terms of the quantum lectures. So before we get to level 3, let's go back and look at what Feynman suggested happens when a particle moves from A to B. So A is just a point, B is another point, and in most universes, well, in our common classical understanding, a particle would then move possibly from A to B. However, we've seen with the multiple two-slit experiments that possibly our universe isn't that simple, and that you can consider a photon or even a particle to go through more than one slit at the same time. So the way Feynman used this, he came up with a way of thinking about things where particles take lots of paths between A and B. And in his, not only his, in that quantum mechanical way of thinking about things that is the underlying force of quantum electrodynamics and quantum chromodynamics and some other quantum field theories, you get to integrate over each path, which means you get to state each path, and each path contributes. So you can say that each path has an amplitude, which we discussed a little, and we can debate the meaning of that, which is related to a probability. So these amplitudes will interfere. They don't just add. And sometimes you get positive interference, sometimes you get negative interference. And you can explain, for instance, the two-slit experiments like this. That particles took all the paths. They took one and the other. And their amplitudes interfered, and you just, when their amplitudes interfered a lot, you got, constructively, you got the most probable endpoints. Otherwise, you got endpoints that aren't very probable. So this is an aside, so now we'll go into level 3, which says that every time you make a quantum mechanical measurement, that quantum mechanical measurement could have gone the other way. So if you had a detector here that had pixels, and this pixel lit up, it could have been that this pixel lit up, even though the experiment was the same. You had a two-slit experiment. Here's your source. Here's your slit plane. And here's your source, your detection plane. Detection pixels, I'll call it. So it's like also you can go to Schrodinger's cat. Let's say you open the box. In one case, Schrodinger's cat's alive. Another case, Schrodinger's cat is dead. Then you get to live in a universe where each of those is true. But each time a quantum mechanical measurement is made, a universe branches off and becomes a different multiverse. And you can't remember the other ones because they're causally disconnected from you. You consider each of these similar to Feynman's multiple histories. So there's a debate. Questions come up. Okay, well, what's the difference between level 1 and level 3? They seem similar, all these different multiverse hypotheses. In both of those, you seem to be able to have the physical constants be the same, whereas in level 2, they were differing, so that one was clearly different. Level 1, and this could just be semantic differences, twins reside far across 3D space, in space and time. So theoretically, a single photon could pass you, and then, a long time later, in your frame anyway, your twin, to a photon moving at theoretically infinite speed, time doesn't pass. In level 3, however, you and your twin are in a disconnected physical reality. Therefore, a single photon could not pass you and your twin. Maybe this is an important difference, maybe it's not. It's fun to think about, though. We can branch out and say level 4. So level 4 is an attempt to be all-inclusive, so there's not an infinite number of levels, because that would get out of control and be less fun to discuss. So you can consider level 4 to be an ultimate ensemble, where all universes that can be theoretically defined for all space-time, for all different constants, for all different measurements, all the differences that humans can't imagine. There, if you throw that in, you should probably cover everything. And it's designed to be so general there cannot be a level 5. It's the 4 level of multiverses. So your twin could be contemplating this right now, possibly thinking the exact thoughts you're thinking, possibly not, possibly thinking something slightly different. This is not beyond criticism. So most multiverses hypotheses, it seems to me, are not falsifiable. However, it seems to me that people who suggest these tend to be a little bit sensitive to these criticisms, and they're constantly trying to find falsifiable claims. So some people think that scientific theories that are not falsifiable, which means they can't be tested, they're no good. They don't help us at all. The idea of physics is to help us predict things, and predict things means you need concrete predictions. And if you don't have, that's falsifiability. You don't have concrete predictions, you're just thinking. You're thinking out loud. So that's one claim. And it'd be great if there were ways to test these. As yet, I'm unaware of a clear way to test a multiverse hypothesis. Also, it is thought that some multiverse hypotheses are needlessly complex, and this is also controversial. Hence, they violate Occam's razor, which says that you shouldn't use anything more complex than need be. However, this has been also debated, and some people think that an entire multiverse theory would be simpler, in fact, than alternatives where you'd have to define lots of things going on in different universes. And with that, I will leave you and all of your doppelganger twins across the multiverses to contemplate this, and I will see you next time.